Okay, so now I'm going to tell you what the simplicial approximation theorem says and why it's useful. So here we have two complexes, A and B, and I have two maps. I have a simplicial map that goes from A to B that preserves the simplicial structure, and I have a continuous map that goes from one point set to another. So the simplicial map looks something like this. It takes a vertex and it maps it onto another vertex. Now the continuous map just takes a point. In this case, we'll say it takes the vertex interpreted as a point and maps it onto another point. This is not necessarily a vertex, while that must be a vertex. So what does it mean to be? We want to capture the idea that the simplicial map is somehow close to the continuous map, because we want to go back and forth between continuous and simplicial maps. And so what we'll do is we'll look at the basic idea is that I want to be able to take the continuous map and slide it just a little bit without sort of exiting the simplex where the point lands and turn it into a simplicial map. So this, if I take the vertex and I look at every simplex that contains it, this is called the star of the vertex. So this blue area here is the vertex, is the star of phi of V, of this vertex here. And this is a fairly common thing. And here, again, the image of V under the continuous map is sitting inside this star, the way that I have drawn it. So let's clean up the picture a little bit. So now I want to go back here and look at this star of V in A. And I want to look at so I know that the simplicial map sends the star here into the star there. Maybe not, maybe it doesn't hit everything, maybe it collapses parts of it. But this whole thing has to map here because it's a simplicial map. So let's look at the image of the star here under the continuous map F. And what we want is we want the image of the star under the continuous map to lie inside the image under the simplicial map. And so that's a way of, that's our notion of saying that these maps are somehow close to one another. And that any property of one, that we can kind of go back and forth between them without perturbing the map too much. So the map phi is a simplicial approximation of the map, continuous map F, if the image of the star is contained in the star of the image. It's this picture right here. Now, what the simplicial approximation says, now it turns out that not every continuous map has a simplicial approximation. It's fairly easy to come up with an example of something where you just have to stretch things too far. So instead, what you can do is if I'm given a continuous map from the polyhedron of A to the polyhedron of B, I can subdivide A. I can chop it up into little pieces, which notice subdivision doesn't change the polyhedron. I can divide it up in little pieces in such a way that the simplicial map on the subdivision is an approximation of the continuous map. So that says that if I want to approximate a continuous map with a simplicial map, then I may have to chop the complex A up into smaller pieces in order to have more control over where the points go. So we're going to use yeah, so this is the Barycentric subdivision, and this is you do it n times. Okay. So it says that may be a lot of times. So it says that you just subdivide and subdivide until things get really, really small, and then it's easy to approximate the map that you want, because you're making the star smaller in A, and it makes it easier to fit inside the star in B. And I've shown this here for the barycentric subdivision, but actually it holds for any subdivision that shrinks the diameter of a simplex. And later on, we'll do the same thing with a slightly different color-preserving subdivision. Okay, so remember we had our definition of a barycentric subdivision. Remember, each vertex of the barycentric subdivision is a face of sigma. And the simplex, remember, is just a set of faces ordered by inclusion. So you could define all of this in terms of partial orders, but we're going to use this geometric picture here. So I'm going to introduce a kind of a gadget that I'll call the truncated barycentric subdivision. And so what I'm going to do is I'm going to take every face of dimension less than n minus k and throw it out. So here I'm going to throw out all the zero-dimensional faces. And so what I end up with is this y-shaped thing here. It's actually more interesting in higher dimensions, but I didn't have time to figure out how to draw that. And so we'll call the truncated barycentric subdivision is just a barycentric subdivision where we throw out all the faces of a dimension smaller than n minus k. And then we'll take that and subdivide it somehow. So I take this and do any kind of arbitrary subdivision. Now,
what's the meaning of the gray thing?
Oh, the gray thing is that we're going to color them in a minute. So to emphasize the fact that they're uncolored, they're now gray. So these things are gray because they're uncolored. This is the missing space. So the simplex here is actually a graph because we've thrown away so many dimensions. In general, it's not a graph. In general, it's a simplex of smaller dimension. But everything with the dotted lines has been discarded. So the next step is going to subdivide that. And now what I'm going to do is I'm going to take each vertex in the survivor thing here and color it with a color from the non-existent corner where it was. So this gets red because it had a red corner. This gets red because the larger simplex has a red corner, and so on. And so this is kind of a truncated Sperner coloring. Now, what I'm going to claim here is that some K simplex has K plus 1 distinct colors in this. So this is kind of an analog of the Sperner's lemma, except we're talking about a truncated subdivision where I've scooped out lots of low dimensional pieces. How do I know this is true? Well, imagine we put all the discarded vertexes back. So I did a subdivision here. So I can put the vertexes back, and because this is all convex, I can just make a kind of a cone over each of these things. And all of a sudden, I'm back with a Sperner-colored subdivision. And I know that one of these n simplexes has n plus 1 distinct colors. But I threw away a piece of that. But what's left, because the n simplex, every vertex has a unique color. If I throw away all but there's got to be some k face here that also has k plus 1 distinct colors. That's the proof. So it's a minor variation on Sperner's lemma. Okay, so that's a combinatorial gadget that we're going to use to get our k-set agreement lower bound. So what I'm going to do is I'm going to build a continuous map from the truncated barycentric subdivision of K to the protocol complex of K. This is assuming that this is K connected, and then the smaller ones are K minus 1 connected, and so on. And I'm going to do this in such a way that for every simplex tau, the image of tau under F is in the protocol complex for P. And then I'm going to use simplicial approximation to turn this into a truncated barycentric subdivision. And then I'm going to use the coloring lemma to show that you can't solve K set agreement because there'll be K plus 1 distinct colors. So again, this is very similar to the proof I gave you for manifolds, except we're no longer dealing with manifolds. But all of these steps are roughly the same. So what we're going to be doing a lot here is we're going to do the proof in an easy case, and then we're going to go over and do the same thing in a more complicated context. So this is the truncated subdivision. So what does this look like? So here, this is the truncated subdivision where n is 2 and k equals 1. And so this is the protocol complex for the entire thing. And then I'm going to look at the protocol complexes for each of the faces of a sigma. Here only PQ, oh that's, yeah, here only PR, here only PQ, and here only QR run. And I'm going to play the same kind of games I did before, slightly different. So I'm going to take, this is, represents an execution where P and Q ran in here. So I'm going to go over to this complex and I'm going to map this vertex here, that vertex there. The one in the center I'm going to go put there. And so how do we know where to go? Well, we look at this vertex and say, well, the corners are P and R, so I'm going to go to P and R. This one, the corners are PQ and R, so I'm going to go to PQ and R. And this will give me a vertex map. Okay, then the next thing is I'm going to inductively assume that the map is defined on the d-1 skeleton.
So what's a skeleton?
Oh, sorry, the skeleton of a complex are all the simplexes in the complex of dimension d or lower. So you take everything of dimension higher than d and you throw it out. So if, so mark that down as a missing slide. So here's a solid simplex. You know, the one skeleton is this hollow simplex. And then the 0 skeleton is just the vertices. So the So this is defined on the skeleton of this complex. So you can think of this. This is kind of this is a kind of a template for the maps that we're going to. I'm going to build a map from a subdivision of this into here, and then I'm going to use that Sperner lemma variant to show that something here has to have all the colors. So we know that that this is deconnected by hypothesis. And so what does that mean? Well, it means that we can fill in each of these simplexes, we can fill it in with a continuous map. So each of these things you can think of, in this case, it's just path connected. In a more general case, it would be a higher dimensional sphere. But we can, each simplex in the D skeleton, if you think of the boundary of a simplex is a sphere. And being connected means I can take that continuous map of the sphere and fill it into a map of the disk. So it says that here I now have a continuous map from here to here. So next what I'm going to do is I'm going to take a simplicial approximation of it. So I'm going to take this continuous map that I know exists because of connectivity, and the connectivity is a continuous property. Now I'm going to use the magic of simplicial approximation to turn this into a simplicial map. So it starts out on a vertex, and each of these blue things is a vertex, but the continuous map could wiggle around in all kinds of ways. But the fact that I can take a simplicial approximation means that if I can subdivide this, then I can push the continuous map over just a little bit so that it hits vertexes. So it carries vertexes to vertexes. So now I have a simplicial map from this gadget into the protocol complex. Now, let's look at the winners. Well, we know that here, P, the winner had to be either P or Q. Here it had, here it had to be P or R. Here it had to be P or Q. Here it had to be Q or R. Here it can be anybody. And so we color this with the ID of the winner, just as we did before. Take those colors and we pull them back over here. And now we have this kind of truncated Sperner coloring of this complex here. And what do we know? Well, we know that over here, one complex has to have k+1 colors. But this is a simplicial map, so that means that that maps onto another complex that has k+1 colors, which means that there's some execution that decides k+1 different values, which means that you could not possibly have solved k set agreement. So basically what we do is we exploit the connectivity of the protocol complex to embed this gadget into it. And then we use the Schwerner's lemma to show that, well, the gadget has coloring over here gets pulled back over here, but we understand the combinatorial properties of colorings here to give us too many colors, which we can push back over here and say there's an execution with too many colors. So the important principle here is that we're mixing combinatorial and continuous arguments all over the place, because when we say it's connected, that's a statement about the continuous structure, that continuous maps of spheres can be filled in. We use simplicial approximation to, so we build this continuous thing, and then we say, okay, now we're going to do a simplicial approximation and transform it from continuous to discrete. And once we're discrete, then we can say things about computations. So this idea that you can go back and forth between continuous and discrete is one of the more interesting aspects of this whole approach. If we tried to do this kind of argument entirely in terms of discrete stuff, we'd be writing something that would be even longer than Nancy's book, because we'd be recapitulating stuff that people in mainstream mathematics have been spending several hundred years doing. So by being able to move back and forth, we can make use of things like simplicial approximation theorems and so on. Okay, so that shows you that if you satisfy this particular combinatorial property, you can't solve case-set agreement. So now, again, this holds for message passing or shared memory.
Can you remind us of the particular assumption?
Oh, so the assumption is that the protocol complex, you start with a global state, an n simplex. Every execution where there's no failure is k-1 connected. That is, every sphere of dimension k-1 or lower can be filled in, continuous map. And then as you introduce failures, that lowers the dimension of the simplex. Each time you drop the dimension of the simplex drops by 1, your level of connectivity drops by 1. Until after you add k failures, you simply demand that the protocol complex be non-empty. So you can tell after k failures, the protocol still halts. That's the assumption. So if this is true, then you cannot solve case-set agreement.
But now you are going to show that in a message passing, asynchronous message passing system, or asynchronous shared memory,
satisfies this. Yeah.
Protocol complexes have these properties.
Yeah. So one of the reasons this theorem is interesting is because there are models that satisfy it. We could also prove theorems that where we don't know any models that satisfy it, but that's. So once again, this level of argument doesn't say anything about irrational model of computation. It just says it's got complex that has these particular combinatorial topological properties. Then you can't solve a particular computational problem. But you're right, the next step is to show, well, actually, there are some interesting models that this theorem applies to something. So again, if the adversary can keep the protocol complex K connected forever, this means that case-set agreement is impossible in that model. If the protocol complex is K connected for a certain number of rounds, as is typical in the synchronous message passing models, then that's a lower bound on the number of rounds. And then in semi-synchronous models, if you can keep it connected for a certain amount of real time, then that's a real-time lower bound on K-set agreement. And there are examples of each of these results in the literature. Okay, so now what I'm going to do is I'm going to show you that this actually applies to read-write memory. And what I'm going to do, this is a fairly long proof, but if you remember the proof that I gave you for the path connectivity, how if the components reach path connected and their intersections are non-empty, then the whole thing is path connected. Well, it turns out there's an exact analog of this for higher dimensional connectivity as well. Although, of course, the statement is a little bit more, it's not much more complicated. It's just we have k clauses instead of 2. So what I want to prove is that I want to show that for n+1 processes, in wait-free read-write memory, you can't do n-set agreement. So you can't do even the weakest form of non-trivial set agreement in this model. You can't get everyone to agree to drop one value. And what we have to show is the property that I mentioned before. For every input simplex, we want to show that P of sigma, that n shouldn't be there. P of sigma is dim sigma connected. And this is a compact way of giving you those K conditions that I gave you before. Because remember, -1 connected means non-empty. -2 connected is vacuous. Everything is -2 connected. So introduce the notion of a covering. So C is our complex. If we can represent that as the union of interesting subcomplexes, we'll call this a covering. So this is exactly what we did when we were talking about path connectivity when we talked about the P sub i's. That was also a covering. So I'm going to introduce something called the nerve of the covering. So given a complex and a covering, where I'm going to define a derived complex, a kind of a cousin, not quite a dual, but a cousin, which is called the nerve of this complex. So each vertex of the nerve is one of the pieces of the covering. So each C sub I, which is a subcomplex of C, is a vertex of the nerve complex. And a collection of these things form a simplex if their intersection is non-empty. So as you can imagine, this is a way, usually a way of greatly simplifying the structure of a complex. So it says that all we care about, if we just think, all we care about is how these components are connected to each other. So where, we throw away the structure of the C sub I and just look at the way that they're interconnected. So here's an example. So I'm looking at again, these are simplicial complexes, although I've drawn them to look like spheres, for suggestive reasons. So this is the entire complex is this sphere-like complex. I'm going to break it up into two hemispheres, and that's the covering of these two pieces. So each vertex of the covering is down here. Their intersection is non-empty because I glue them together along the prime meridian here, so there's an edge between them. So this complex, you can see, has lots and lots of simplexes, and it's fairly complicated, but this nerve complex is much simpler. So that's the covering, and that's the nerve. If I chose a different covering, I get a different nerve. So the nerve is not a property of the complex, it's a property of the covering. So there's a classical result called the Nerve Lemma.
Why nerve?
I don't know. This is what they call it. It was probably French or German or something and mistranslated. I don't know. I don't know where the word comes from.
You look at the other parts of my body and the connecting between them.
It looks like a nervous system.
Yes. That's the intuition.
Yeah, yeah.
Maybe tenemos the gallo.
You could mistranslate it as the chutzpah lemma. Okay, so this is the nerve lemma, which is a classical theorem which we are certainly not going to prove. So it says that if each component is itself K-connected, so if we manage to decompose it into pieces that are individually K-connected, and if I take the intersections of every set of size, every set U of a particular size, then that is K minus U plus 1 connected. What that says is that each one is K connected. I take their pairwise intersections. The intersection, the connectivity drops by 1 level. And then I take the intersection of all 3 of them, then it drops by 2, and so on. And then, so if each of these intersections, which remember is non-empty if it's a simplex, if that's k connected and this is k minus 1 connected, and notice the similarity between these conditions and the conditions I gave you for k-set agreement, where it's talking about the smaller and smaller simplexes, the connectivity goes down. Here we have bigger and bigger intersections, which means smaller and smaller components, and the connectivity goes down. This is not a random coincidence. Okay, and then under what given that we have that, that's our hypothesis, then it turns out that C, the union of these, is k-connected if and only if the nerve complex is k-connected. So this is a little bit complicated because it says that if we have this precondition, then it turns out that the connectivity of the entire complex is the same as the connectivity of the nerve. So we can
Go back to 105?
So the precondition says that if each individual one is k-connected and their intersections, the connectivity drops by the size of the intersection. If this is true, if we establish this as a precondition, then instead of reasoning about the connectivity of the complex, we can reason about the connectivity of its nerve, which is an improvement because the nerve is often much simpler than the original complex, if you pick your covering right. And in fact, the nerve is exactly something that arises naturally when when we looked at the path connectivity case, when we were talking about the fact that if you're path connected and your intersections are non-empty, that is the degenerate case of the nerve theorem, where we're talking about being zero connected. So this is a direct generalization, raised to higher dimensions of the arguments we already did. Okay, so let's do an application. So each of these, each hemisphere is basically a disk. This is topology, so we can do this sort of thing. And each of these is one connected. If I put a string around, any map into the disk can be filled into a map of the disk. So each of these things is one connected. And the boundary is zero connected. So that means that the nerve theorem applies for k equals 1. And so what that says is that we can apply the nerve lemma, and we know that this complex is one connected, pretty easily. And that implies that the sphere is one connected. Now, you probably already knew that the sphere was one connected, but this is the proof.
K plus 3 does.
Beg pardon?
For K plus 3, this one is pre-connected as
For k, for k equals.
yes, because and you can feel the.
For higher dimensional spheres, yeah. Okay, so that's, it's not really proof, but it's close enough. Okay, so let's, inspired by this machinery, let's go back to talking about computation. So remember that, so let's say a protocol state S, we're going to go back to talking about how protocol complexes evolve over time. So we'll say S is not a simplex. It's a protocol state, which is everything we need to know about the processes and the environment. And there should be a close parentheses there. And then where S is a protocol state, P is going to be the reachable complex from that state. So initially, before anything happens, the state is the same thing as an input simplex. And then, but as things go along, as we showed you before, the reachable complex shrinks. And we'll use S as kind of a bookkeeping device for keeping track of how you got there. So we'll use the same notation that we used when we talked about consensus, where we have a protocol state S, and we'll say S sub I is the new state if P sub I takes the next step. So we're in a state, there's a number of processes that could take a step. If the scheduler says P sub I takes a step, then the state goes from S to S sub I. And the reachable complex goes to this, which we'll abbreviate as big P sub I, just to keep the notation under control. So that's the reachable complex if P goes next, and that's the our notation. Okay, so to build up some intuition before we start to getting all symbolic and everything, consider a three-process case where you have shared memory. And the colored thing is the reachable complex. This is what's reachable if 0 goes first. This is what's reachable if 1 goes first, and this is what's reachable if 2 goes first. And there are only 3 processes, so somebody's got to go first. So this is a covering for the reachable complex. In this case, you know, there's these three possibilities. So let's say that, to make the example more concrete, P sub 0 is about to read a value u from memory, from a particular memory location. P sub 1 is about to read that same value from the same place. P sub 2, however, is about to write a different value to that memory location. So everyone is, you know, so it's like an old Western movie where everybody is, you know, ready to shoot. The P sub 0 is about to read, P sub 1 is about to read, and P sub 2 is about to write. And these are, you know, the various reachable complexes if each of these things happens. So let's look at the two readers. So here P0 reads first, here P1 reads first. Their intersection is every state where P0 could have gone first or P1 could have gone first, and no one can tell the difference. So a vertex in here is one where you can't tell whether P0 read first or P1 read first, where nobody who's running can tell. Because you're reachable if P0 goes first and you're reachable if P1 goes first. So it's got to be ambiguous, because if you could tell the difference, you wouldn't be in the intersection. So what does this intersection look like? Well, what I claim is that, so S01 is the state after P0 and P1 both read. So P0 is the reachable state after this happens. And because reads commute in some sense, nobody can tell who read first. What that says is that this intersection here is actually the entire reachable complex from another state. So this has kind of a nice structure. It just says that if you want to know what the intersection of these two things look like, well, let them both read in either order. You know, either like that, and then look at everything that could possibly happen. What about intersections of readers and writers? So here P0 moves first and it reads U, and P2 moves first and it writes V. So what are the executions that can't tell which of these two things happened? What are the what could happen here where you can't tell whether P0 read or P2 read? Well, P0 knows the difference, because P0 either read U or read V. So it's like in a mafia movie, you have to kill the witness. So these are executions where after P0 reads, it doesn't take any more steps. So you can maybe think of it as it either crashes or it doesn't take any steps until everyone else finishes. So this is an execution where P0 does not participate. So what we do is we can just crash P0, because if it crashes, we don't care whether it reads or not. And then we just let P1 basically run by itself. So actually, this should be a 0. So I want to say you take the same state and you just throw out one process and don't let it take any more steps. Okay, so the pattern here is that the intersection of P0 and P1 is a protocol complex with fewer pending operations, where you just it has fewer processes. The intersection of the intersection of the two readers, it's just a protocol complex for the same number of processes, but you just sort of move slightly on. If they conflict, then it's a protocol complex with fewer participating processes. So in one case, we have the same protocol starting from a later state. In another case, we have a smaller protocol with fewer participants. But in both cases, they're reachable complexes for a read-write protocol. Now, what time is it?
5 minutes.
5 minutes. Okay, so anyway, so this suggests an inductive argument. So I'm not going to launch into this whole set piece battle, operatic presentation because I don't have time. So I'll just say a few words about what's going on next time. So like as before, I'll review this next time, so don't panic that you'll have forgotten this by next week. So as before, we'll say the P sub I is the reachable complex from some state S if Pi takes the next step. We'll take an arbitrary set U, and if we take the intersection of these things, these are all of the views of executions in which some process in U went first, but you don't know which one. And so we'll need to think about executions here. So an execution is just a sequence of process steps. And at the end of an execution, the views of the non-faulty processes determine the simplex of the protocol complex. So you can look at an execution, and at the end you say, well, this is my view that determines a vertex. And so we can say that two executions are equivalent if they determine the same simplex. In other words, nobody can distinguish between them. So from the outside, you might see that the two reads happen in this order, but none of the participants can tell what happened. So we'll look at non-conflicting operations. As in the first case of the example that we looked at, P writes you're reading something and nobody writes at the same location, or you're writing something and nobody reads. Because we have a multi-writer, single-writer memory, we don't need to worry about writes conflicting because you always write to disjoint locations. If we could do without that assumption, and the proofs would just grow a new case and get slightly longer, but we don't care about that. And otherwise, we'll say the operation is conflicting, and this is a case analysis. So we say, well, what happens if there's no conflicting operations in a particular state? Then one thing happens. If there are conflicting operations, then we do something else. And so what I'll do then is show you a number of lemmas about things. And then what I'll say is I want to show that the protocol complex is basically n-1 connected, and so on. I'll assume it's false. We'll find a critical section, a critical state. We'll get to the critical state and say, well, notice that all of the possible next states form a covering. I'll use these lemmas here to show each of these coverings has to have a high level of connectivity. And show because of this, we can apply the Nerve Lemma. And it turns out that the nerve of the protocol complex is extremely simple. It's just a big simplex, which is as connected as you want. And then by application of the Nerve Lemma, that will give us the fact that the protocol complexes for the read-write model satisfy the conditions of the theorem. Therefore, you can't solve an set agreement. And so I'll show you how to do that next week. And then we'll move on to we'll go from models of computation to looking at specific tasks of interest. So we'll look at something called colorless tasks, where we can prove lots of interesting theorems relatively easily. And then from that point on, we'll move on to non-colorless tasks, which will require a little bit more machinery to prove some things. Okay, next week.